Okay, I'm back. Just give me a couple minutes both to let everyone else get back and for me to reset up. Okay, so very good. Looks like I got most of you back and things are working again. And make sure everyone can see my screen and hear me. You could raise your hands again. Okay, very good. Sorry about that. Hopefully, if the tablet crashes again, I will just have to make do without the tablet for today, but it's kind of important for today, so hopefully it won't crash. Okay, so basically there's two ways we store databases these days. One is on magnetic disk drives, which are being phased out in favor of solid state devices, which are faster, but for the foreseeable future, both will be being used. Solid state devices have much faster access times than magnetic disk drives, so they will ultimately win out. But right now they are more expensive than magnetic disk drives. So I'm not going to get into specifics. The book did a nice job, but just a few things. Both magnetic disk drives and solid state devices essentially store rows into blocks. Now, solid state devices might call them pages. Whether they're called blocks or pages is really immaterial. The point is that you have some conceptual block, I'll call it block, that has some number of rows in it. And we are going to assume that it's rows that get stored in the blocks rather than stored by columns. So we're assuming row oriented, and we have some number of rows in a block or a page. And when we read from a disk or from a solid state device, we read a block. So we actually end up getting more than one tuple. We end up with several tuples that we get. And it is much slower to go to physical memory, whether it is a solid state device or whether it is a magnetic disk drive. It is an order of magnitude slower to get the data from one of those devices than it is from main memory. So we will do pretty much anything we can to minimize the number of blocks we have to read in order to satisfy a query. So before we get there though, there's a couple more things we have to worry about, which is what costs us when we are going out to these things. The first thing we worry about is access time. And that is the time required to get to the first, to get to the point where we are ready to start transferring data. And then, so it's the time required to reach the first block we will read. And then there is transfer rate, which is the rate at which we can read blocks into memory. So with magnetic disk drives, we have to go further, and there's two concepts called seek time and rotational latency. Which the book did not really go into, and which I will. So on a disk consists of a bunch of platters, and each platter has some number of rings on it, which can be called sectors. We'll call them sectors. And then on each sector, that is divided into our blocks. So seek time, so you have a read-write head. And so if you take a look at this from the side, what you would see is a spindle with some number of these disks on them. And you'd have a read-write head that is moving in and out on this spindle from the center outwards, getting to the right sector. So the seek time is the time it takes the read-write head to reach the appropriate sector. So seek time is the time required by the read-write head to reach the correct sector. Okay, the sector containing the first block we want to read. Then when we've reached the right sector, we still have to rotate to get the appropriate block under the read-write head, and that is what rotational latency is. Is the time required for the appropriate sector or appropriate block to rotate under the read-write head. Okay, so these times have leveled out recently, and in general, what we can say is that the seek times are 3 to 4 milliseconds for high-end devices, 9 milliseconds for your average desktop hard drive, and 12 to 15 milliseconds for your average mobile device, which includes your laptops and your smartphones. So these are seek times for disk drives. And they have stayed pretty steady probably for the last decade now. They really haven't sped up very much. And then rotational latency tends to cost you another 2 to 7.15 milliseconds, so you're basically looking at something of the order of 6 to 20 milliseconds for access time when you add those two together for a hard drive. For a solid state disk, it is closer to it's generally, so this is access time for a disk. For a solid state device, it's much less. It's generally less than 1/10 of a millisecond, because all it has to do is seek. There's no rotational latency. It's all seek in terms of trying to get to the right block. So solid state devices reduce the access time considerably. And then they also considerably speed up transfer rates. So the transfer rates for hard drives, good consumer ones are about 200 megabytes per second. Consumer grade, good consumer grade. Enterprise is closer to 300 megabytes. For solid state, the transfer rate's much faster. They actually start at a minimum of 200 megabytes, going up to 2.5 gigabytes per second. So you can see why solid state devices are taking over. They're just a lot faster than hard drives. So there are, however, a couple drawbacks to solid state devices. So say solid state device drawbacks. So first of all, they're about 12 times more expensive right now. Per gigabyte. It's about 24 cents right now versus about 2 cents for a hard drive. Second thing is that writes can be 10 times slower than read times. So write times can be 10 times slower. So if you looked at that transfer rate, it might be down to only 20 to 250 megabytes per second write times, which might be even slower than on a magnetic disk. Okay, now with enterprise grade, they are the same. So enterprise grade read and write times are comparable. But of course, you pay more for them. The solid state devices in your phones and laptops are not enterprise grade. So your write times will probably be 10 times slower than your read times.
You might also be able to consider the fact that SSDs, as far as I'm aware, they have their lifetime is in a write tolerance. You can only write to certain cells so many times before it's pretty much dead.
That's a good point.
Which I don't think is the case for disks.
Yes, so another good point, another drawback of SSDs is they have a limited number of writes typically before you can't do it anymore. So limited lifetime writes. I think it's to a particular cell, right? Not.
Yeah, each particular cell has only a certain number,
Yeah.
but that's actually going up pretty good. I've seen some where it looks almost infinite. It's like petabytes. It's kind of
Right. I
ridiculous.
remember that it used to be the rule of thumb was you could keep one for about 5 years. And this was
Yeah,
a few
that's what I
years
heard
ago.
too.
And I forgot to look it up this time what the suggested lifetime is now. So you're right. I think it's going up pretty fast on that.
Yeah, the Octane, Intel's Octane, whatever you call those things, they have like 5 petabytes of write tolerance. So it's basically immortal. I mean, petabytes.
Right. That would seemingly be pretty, unless you had something that had tremendous transactions being written to it, you would be in good shape. Okay. So good point. Okay. So the big thing though is these transfer rates are minuscule compared to what you can get out of main memory every minute. So the transfer rates out of main memory are going to be at least 10 times higher than the transfer rates off of the disk, or it's not going to be quite as good over SSD, but it's still going to be several times faster than off of SSD. So what we want to do, the gold standard is we need to minimize, our goal is to minimize the number of block accesses. And we'll often pay a considerable number of in-memory instructions to minimize the number of block accesses. Okay, so when we are choosing a file organization that we can use for a relation, we have essentially 3 choices. So basic file organizations. The first is a heap, which is an unordered collection. You basically just store them one after another on the disk. You almost never use this because of how inefficient it is. Since the file is unordered, essentially the only way you're going to be able to find something in it without an index is a linear search, which means you read the entire file. So it's very unusual to use a heap. The only time you might use it is for very small files. So I'll just say works for very small files. Okay, there are such files. So in our branch relationship, in our leasing company, the branch relation, we're just not going to have that many branches. So if you think about the fact that most blocks are 4,096 bytes, okay, so blocks are generally about 4,096 bytes. If you consider that maybe there would be 100 bytes at most per tuple for a branch, then you could fit about 40 of them. You could fit 40 tuples into one block. And because we very well, unless we're a huge property management company, we probably don't have this many branches. So probably we could fit the entire branch relation into one block. Therefore, we would probably use a heap for the branch relation. Okay, so it works very well for small files. Okay, second one is for B+ trees. And it works when we want to be able to cluster on some attribute. So allows us to cluster on some attribute and supports and efficiently supports range queries. By a range query, I mean something where I'm saying I want something where A less than equal X less than equal B. That's a range query. I want all values, all tuples where X is between A and B. And B plus trees, I shouldn't say B plus plus, just B plus trees, they're a generalization of binary search trees, which we'll get to. And then the final one is extendable hash tables, which are also a variation of hash tables. And they are good for point queries. So a point query is something in the form X equals B. It's asking for a single data value, all tuples that are equal to one specific value. So these are the three basic types of file organizations that we can choose from. And for the most part, we tend to organize our files using B plus trees because we almost always have some attribute that we might want to be able to perform range queries on. So for example, and it's usually not the primary key, interestingly enough. So the primary key is often an artificial key, and it makes no sense to do a range query on an artificial key like hotel number. But it might make sense to do a range query on a person's last name, like give me all people with the last name of S. Or if I have a race results database, let's say I have race results from running a race, then I might have runner ID as the primary key, but it's really meaningless, whereas the race time means a lot because I may want to get all runners that finish the race in less than 15 minutes or in more than 20 minutes. Or I used to be a competitive runner. I used to like to know who were the runners near me. So I might ask who are the runners who finished the race between 16 and 17 minutes. So in this case, while the primary key is the runner ID, I would actually cluster on the race time. So I would actually sort the B plus tree would actually be sorted on the race time rather than on the runner ID. So that's just an important thing to know, is that oftentimes when you use a B plus tree to organize or store a file, a relation, you're not actually sorting it on the primary key, you're sorting it on a different attribute that's more likely to be involved in a range query.
Dr. VZ?
Yes.
Just to be 100% on that, when you're saying allows us to cluster on some attribute for B trees, are you saying that, are you meaning that means contiguously
Yes.
lay out the memory? so that you can
Yes.
bring it in similar blocks, like with caching and stuff.
Yeah. So when I talk about clustering, what I mean is that I sort and contiguous sort and contiguous tuples are stored in contiguous locations on the disk, or I'll call it secondary storage, so that I don't say disk or solid state device. So yes, so we sort it on that attribute, and then we store them. The contiguous tuples are stored in contiguous locations. Now, we can't assure that it's completely contiguous in the sense of an array. As you will see, the blocks will end up scattered around secondary storage. So it's only the tuples within the same block that are stored contiguously. But nonetheless, if it may well be that if 15 tuples satisfy the result, we only have to read one block, okay? Or if it's even, say, 200 tuples over 5 blocks, at least we only have to read 5 blocks, whereas otherwise, if they're scattered all over, we might end up with, if we have 200 tuples, we might read 200 blocks. So yes, the blocks aren't stored contiguously, but at least within a block, you have contiguous tuples. Does that make sense what I'm saying?
Yes, it does.
Yeah.
And when we bring those into main memory, because of the way the query works, the blocks end up, say we need 5 blocks for the query, they end up being contiguous in main memory, even though on the secondary storage, they might not be contiguous.
Yes, that's a good point too. So as you read those blocks into main memory, you can ensure that in main memory, the blocks are contiguous. For example, on a cache line, you might be able to read them into cache lines and keep them contiguous. Okay.
Okay, that makes sense.
So just quickly, a quick review on expected running times. With a heap, to find something is going to generally take order n, where n is the number of tuples in the file. With a B+ tree, we're going to find that it's going to be log m divided by 2n, where m equals number of tuples per interior node. And we'll get to that when we get to B+ trees. And then for extendable hash, it's going to be roughly order 1. And we'll see that more specifically, that tends to be 3. Specifically 3 is the number of maximum number of disk accesses required. So the reason we use B+ trees as our organization, again, there's almost always one attribute that can be profitably sorted on. Therefore, that is why we tend to at least store the files as B+ trees. But again, very, very small files tend to be stored as heaps. Okay, questions about that? Okay, so that gets us through how we can store them. The next thing is indices. So the book gave a nice example of indices. I'm not going to go through the pictures with them. I assume that the book did a nice job of showing how, for example, if you have a 1 gigabyte file and an index that's only 100 megabytes, then even if you had to do a linear search of the index, you would only have to look at 100 megabytes rather than a gigabyte. And in fact, our indices will also typically be organized as B+ trees or extendable hash tables. So in fact, the number of block reads is going to be considerably less than even the 100 megabytes. So having a well-chosen set of indices can significantly reduce the time required to retrieve the tuples that satisfy a query, because without the indices, we're probably going to have to do a linear search of the file, or at least with a B+ tree, even if we have a B+ tree as the underlying organization, it will only be fast for the one attribute that we are clustering on. For example, with that race results relation, it only works for the race times. It won't work for efficiently finding the racer's ID because they're scattered all over the file. So indices give us a way to quickly locate blocks and retrieve them. And there are 3 types of indices. There are primary indexes, which means that the index, well, in this case, it means the file itself is physically clustered. Using the primary key. That is pretty uncommon, as I said, because usually the primary keys are artificial. It could be a cluster index, which means the file is physically clustered on an attribute other than the primary key. Or it could be what's called a secondary index, in which case it's an index on a non-clustered attribute. So normally we can have at most 1 primary or cluster index. So at most 1. Because you can't do it, you can only physically organize the file once. Okay, whereas you can have as many as you like. So ideally, our secondary indices are implemented using extendable hash, because they are faster than B+ trees. Now, it turns out that MySQL does not support extendable hash tables. It only supports heaps and B+ trees. So secondary indices in MySQL are implemented using B+ trees. But in SQL, like Oracle SQL, you have the choice of B+ trees, extendable hash tables, or heaps. You typically use an extendable hash table for a secondary index. Okay, and then the book also made a distinction between a sparse index and a dense index. And this only applies to clustered files. So on a sparse index, you have only 1 entry per block. Whereas in a dense index, you have 1 entry per tuple in the index. So I should say 1 index entry per block, 1 index entry per tuple. So generally, cluster indices and PK primary key indices are sparse. And secondary indices are dense. Okay, because with a cluster index, you'll see when we get to B plus trees. I won't try to show you now. I'll show you when we get to B plus trees how you only need to have 1 index entry per block. And hence that also saves on the number of entries that are required. Okay, so again, these are the types of indices: primary, cluster, or secondary. And then you can have either sparse or dense indices. So then the next thing to consider is what to index and what not to index. Okay, so these are things to index. Okay, so we index the primary key. If it's not used to physically organize the file, then we use a secondary index for it. Okay, because we're often going to do joins using the primary key. Even if it's an artificial key, we're going to frequently be doing joins. So we want to be able to efficiently retrieve a primary key. Okay, for the same reason, we want to index foreign keys, because they're going to be frequently involved in joins. Okay, we want to index attributes heavily used in selection queries. So names are, when I call up, one of the first things people often ask me is my name. So names tend to be fairly heavily used in selection queries. Street addresses, I'm often asked for my street address. And for medical records, I'm often asked for my date of birth. So these would all be things that might be that you might put an index on. Okay, anything, so attributes frequently involved in sorts. In sorting queries. So that includes order by, group by, union, intersect. So basically the set operations. If you have select by distinct, all of those involve ordering. And so you would typically put an index on those kinds of attributes. Then attributes used in aggregate operations. For example, salary is often, you're going to do stuff with salary. What else might be? If you had the number of, let's see, what else? Maybe if you have number of days occupancy. I know that this is often computed, but if it was in your index, if it was physically stored, then that would be something you would often put. And the reason that you do that is that you can often use what's called an index-only plan to complete the query. So if I ask for the average salary, if I have an index on salary, I can actually compute the result without going to the physical file. I only have to look at the index because that has all the salaries in it. It even is going to have multiple pointers. If there's 5 people with the same salary, it'll have 5 pointers to the 5 people with different salaries. So I'll know that there's 5 people with that salary. So these index-only plans are very useful for aggregate operations because often an index is all that is required to satisfy a query involving an aggregate operation. So those are things that we often index. Any questions about that? Okay. Then there's also things we don't want to index. Okay, small relations, which would typically be stored as a heap. Because in that case, if there's only 1 or 2 blocks, you just read the relation and do a linear search. Remember, all we care about is number of block operations. We don't care if we do a linear search in memory through the tuples of a block. A linear search in memory of a block is still much, much less than the time, okay, the time for a linear search in memory of block is much, much less than the time to retrieve the block. From secondary storage. So we're more than happy to do a linear search in memory of a block. So we don't index small relations like the branch relation in the property leasing case study. We would probably not index any of its attributes. It's just not worth it. Okay, and attributes that are frequently updated. Because not only then do you have to update the tuple in memory, but you have to update the index as well. And because the attribute value is changing, it's not simply a matter of changing the attribute value. The attribute's location might change as well. For example, if it's a hash table, then when the value changes, its hash code changes, which means it's going to map to a different entry, perhaps, on the disk. So changing an attribute may require changing multiple blocks of the index as well as the underlying relation. So for example, date of birth is not frequently updated, nor is our name or our street address. But for example, inventory is. If I'm keeping track of the number of items that are currently available, that's probably frequently updated, especially if you're a site like Amazon. So quantity would probably not be an attribute you would want to. So I'm going to say quantity of some product is probably not something that you're going to want to index because it's changing frequently. Okay, attributes where the query will retrieve a significant portion of the relation. So for example, position, there are probably not a huge number of employee positions in the company. So if we do a search on position, we're likely to get a fairly large number of employees, which means it's probably not worth it to index it. Now, you might give consideration to putting a cluster index on the employee position. If there's no other attribute in the employee relation that really would be good for a range query, then you might say, okay, I will put a cluster index on the employee position, because at least in that case, even though it's a point query, all the tuples that are a manager will be together, contiguous. All the employees who are an IT specialist will be together. So at least you'll just only have to look at those blocks. So it's possible you'd put a cluster index on it if there was no other good attribute available for doing the clustering, but you wouldn't generally put a secondary index on it. Now, this is something you got to be careful with. You need to know kind of the expected value or the expected number of records per block that are going to be retrieved. So if the expected number of records per block, which remember is tuples per block, is going to be roughly 1, you're thinking, that's pretty good. Only 1 tuple per block. That's like maybe if there's 100 tuples per block, only 1% of the employees are getting retrieved. But that's not the right way to think about it. The right way to think about it is that implies that every block will be retrieved. Okay, if you expect roughly 1 record per block to be returned by the query, it means that roughly speaking, every block will be retrieved, and so that's not a good candidate. Okay, so what you want is that the expected number of records per block should be much, much less than 1. That is a good index, good for indexing. Okay, is that clear? Because that's really important. A lot of students will think that 1%, that if you're only getting 1% of the database, that must be a good attribute for indexing. But that's probably not, because you're probably got roughly 100 tuples per block. So 1% of the database means on average 1 record per block in that case. So is that clear? Not getting any questions. Oh, go ahead.
Well, I was just going to say that's good, because the whole point of indexing, and I assume we're talking about sparse indexing, is to use the index to quickly get to a block. Yes. And then you can do the block scan.
Exactly.
Within the block. And if you're just going to do all the records in all the blocks, which is basically a full table scan, the overhead of the index isn't worth it anymore.
Exactly. You got it. In fact, It basically doubles the cost of the query, because you're going to go through the entire index, and then you'll probably go through the entire file as well. So it'll actually be worse in that case. Yes. So your reasoning was exactly right on. Okay. So then the fourth one to avoid is index attributes involving long strings. And the reason for that is that attributes involving long strings may very well represent the bulk of the underlying relation, which means essentially you're storing the underlying relation twice. So for example, if I have a tuple that's 100 bytes and one attribute that takes up 75 bytes, I probably don't want to index it because essentially if I index it, I'm going to be storing the underlying relation a second time. So I'm effectively doubling the storage of my relation. Now, this comes up against the fact that the attributes involving long strings may be things like street address or name that are frequently used. So this is the idea of what to index and what not to index is very subjective. You often have to play with it once the database goes into production because it's not always clear how the performance is going to be affected by which attributes you index and which you don't. So you can certainly see here that, especially with number 4 on what not to index and number 3 of what to index, heavily used in selection queries, you may get conflicting things about whether to index it or not. And in that case, you just have to figure out which is more likely. Is this attribute so frequently used that it's a good idea to index it even though it involves a long string, or is it just likely to waste a lot of space? If it's a name or a street address, most likely you should index it. If it's a description of something like a course description in a course catalog, a course description probably should not be indexed because it's unlikely we're ever going to do a query on a course description. Same thing with a video catalog. We have a description of the video, a synopsis of the plot. It's unlikely we're ever going to do a search on that synopsis, but it's very likely that that synopsis takes up a big chunk of memory. So that's an attribute we wouldn't index. So while indices improve performance, you don't want to just indiscriminately pick indices because they still have to be updated. They still take space. So just remember, indices take space. Okay, they must be updated. So their cost is not trivial, okay? So there are costs associated with them. Remember, there are costs associated with indices. So you don't automatically index every attribute. There's also times when you might choose multi-attribute indices. So there are multi-attribute indices. A good example of a multi-attribute index would be in the room relation for our hotels. The room number by itself doesn't bias anything in a hotel because the room number may refer to any number of hotels. And similarly, the hotel number doesn't uniquely give us a room in a hotel. So in this case, we would probably choose to index a 2 attribute index on room number and hotel number. So there are times when you choose a multi-attribute index, and that would be most common for when those attributes form a primary key or a foreign key. So there are times when either the primary key or the foreign key is a multi-attribute key, then you would tend to choose a multi-attribute index for it.
Dr. VZ?
Yes.
Sorry to interrupt. Going back to the expected number of records per block, I just thought of something, and I'm just curious. You said much less than 1 is the thing that makes the index worth it. However, I just thought about you're still, even if you're only doing a couple of tuples or records within the block, aren't you still retrieving that block from the hard disk? So even if it's less than 1, you're still doing it for every block. Therefore, all the blocks still end up being retrieved from just secondary storage, versus if it's 1, it's the same number of blocks still end up getting retrieved from storage. So I'm trying to reason out what the benefit is again to the less than 1.
Okay, so let's say, let me give you an example. So let's say that there is 1,000 blocks in our database, and there's 100 tuples per block. Okay, and let's say that the query will do 2 things. Query retrieves 1,000 tuples. Okay, so that's roughly 1 per block. And now we're going to have it retrieve roughly, we're going to have it retrieve 5 tuples. Okay? So in the first case, the expectation is that we're probably going to have to retrieve all 1,000 blocks. Remember, that was the size of the relation. It took 1,000 blocks to store it. So query 1 is probably going to require us to retrieve every block in the relation. Query 2 is only going to require us potentially to retrieve 5 of those blocks, not 1,000 of the blocks. So in query 2, if we have an index that allows us to only access 5 of the blocks rather than read 1,000 of them, that's a huge win. It's going to be about 200 times faster to execute the query with an index than by linearly reading through all the blocks of the relation.
Okay, I think I see where my confusion is. The notation says records per block, which makes me think all blocks. So actually, your number 1 makes me think of 3A, where it says much less than 1, because the number of records is just 1 per block. And there's, I forgot how many you said there were. So that's still less than 1. Right, there's 1,000 blocks, and you're only retrieving 1 tuple per block.
Right.
And like I said, I forgot how many tuples you said per block. It might not be much less than 1, but it's definitely less than 1. But you're saying that notation doesn't necessarily mean all blocks are in the running.
Well, what I'm saying is that if the number of tuples being, okay, so what I mean right here is so expected records, it's, okay, so what I mean by this is look at the number, okay, when I say expected records per block, let me define that better. Expected records per block, what I mean by that equals the expected equals number of tuples query is expected to retrieve divided by the number of blocks. That's what I mean here. So in the first case, I said the query retrieves 1,000 tuples. So we're saying it's 1,000 divided by 1,000. So on average, that query is returning 1 record per block. In the second case, the number of tuples retrieved by the query is roughly 5. The number of blocks is 1,000. So now we're down to 0.005, which is much less than 1. So that's what I was meaning by my notation.
Oh, okay, yeah, that's just the total number of blocks versus the records requested.
Mm-hmm.
Okay, gotcha.
That's why I said it's very easy to look at a query and think it's not retrieving that many tuples, therefore an index would be good. But it's actually not the tuples we care about, it's the number of tuples per block we care about. The expected number. That's what really matters.
Okay, gotcha.
And by tuples per block, you're saying how many tuples we store in each block, not how many we retrieve from the query.
No, what we're worried about is what is the expected number of tuples we will retrieve from each block for that query. So if we retrieve 1,000, if the query is going to return 1,000 tuples, we would on average expect that each block would contain one of those 1,000 tuples if the data is randomly distributed across the file.
But it could be the case that for 1,000 tuples that we want to retrieve, since there's 100 tuples per block, we actually could only be looking at 10 blocks.
That's only if it's a range query. So you're absolutely right. If it's a range query, then it's you're absolutely right that you would in that case be probably putting a cluster index on it. But if it's any other type of query, which is generally a point query, now the records are generally going to be randomly scattered around the database.
So this is really just, it's like
really
big O complexity for retrieval. Yeah, it's like worst case scenario for what we're retrieving. It may not always be that, but it's the big O of retrieval effectively. Yes. Is that correct?
Yes, effectively. Except here it's, yeah, in some sense it's the big O of retrieval and that, yeah, I guess another way to think about it is if you think that even with indexing, if you think that even with indexing, order n blocks will be read, where n is the number of blocks, then the index is probably worthless. But if instead it can reduce it to order 1 to a constant number of blocks, then it's worthwhile. So that may be another way of thinking about it, that even if you use the index, if you end up reading basically all the blocks in the file, the index is worthless. Whereas if it can restrict the number of blocks read to basically a constant number, then it's worthwhile.
Would it be fair to say like the goal of indexing is to minimize the number of blocks read while still getting all the data required for a given
Exactly.
query?
That would be a perfect way to state it. That would be the way you just stated it, that you want The goal of indexing is to minimize the number of block accesses while getting all the data that is required. That's the perfect way to think about it. And if in this case, where indexing still essentially results in your reading almost the entire file, that hasn't really done you any good. Remember, it's not free to read blocks from an index. It also costs you each, many indices cannot be stored completely in memory. So when you look at it, as we'll see when we look at both B+ trees and extendable hashing, it turns out with both of them, you have to read generally at least 2 blocks from memory. I'm sorry, from secondary storage. So the index is not free either. It's going to cost you something. So, yes, basically this is the thing. You're going to index when the index will result in a constant number of blocks being retrieved. You won't index an attribute if it essentially makes no difference because you still need to read the entire file.
So, okay, so, and I believe I definitely get what you're saying, but just to make 100% sure on this one point, the whole average worst case scenario of number of tuples expected to be retrieved divided by number of blocks, having that average out to be mostly include all the blocks, that doesn't happen with range queries where I guess the attribute you're searching for is sorted.
Yes.
To where you automatically know, it's block after block after block. It's only 10 blocks over out of the 1,000. You're done.
Yes.
Then indexing really helps.
Yes, that's right. Even now, if you're going to retrieve, say, 1/10 of the file, if you're searching on employee position and 1/10 of your employees are call representatives, then that's fine. Still, retrieving 10% of the file is much better than 100% of the file. So yes, this analysis really deals with secondary indices, okay? So if I can come back to what we index, what we choose to index and what we choose not to index, this analysis almost exclusively applies to secondary indices. Okay, so I'll even say this really applies to secondary indices. And the same thing here applies to secondary indices. So for a cluster index, what you care about is it a range query? Yes or no?
Okay, so.
Or are there a whole bunch of records that are likely to get clustered because I do it? Is that going to somehow benefit me?
So I'm trying to think of the terminology that Zybook used. God, if I can remember correctly, primary is sorted. Primary indexing is sorted. Clustered, or excuse me, oh my God. Okay.
I think they use sorted for both cluster and primary, if I remember correctly.
Right, but one of them's unique and one of them's non-unique.
Yeah.
That's what makes it different. But the secondary is not sorted. So that's why these things to index apply to secondary, because we don't have to worry about blocks being, contiguous like that with our range queries.
That's right.
Okay, I gotcha.
So, yes.
That actually helped a lot. Thank you for going over that.
You are welcome. Good question. Okay. So, yeah, and I'm sorry, the book uses somewhat different terminology. The problem is, I think what the terminology the book used isn't the commonly accepted terminology. So that was really unfortunate. So I was just trying to was using the more commonly used terminology. Okay, we are out of time. So I'm still free to take questions, but I'm going to let you all go here. On Thursday, we're going to talk about B+ trees and extendable hashing. So we're actually going to talk about how those two data structures are implemented. So that's Thursday's topic. Also remember, I have office hours today from 2:45 to 3:45. And I will see you all on Thursday.